Okay, well, we're going to have a go at this again in a different situation. This time we are going to use good old Ohm's law as our measurements, and of course volts, amps and resistance. Now I know volts is supposed to be E and amps is supposed to be I, but just for the sake of simplicity and for maybe new guys or girls that are starting to get in this sort of experimenting, we will leave it simple. Anyway, there's been one thing bugging me, and it's been bugging me for a very long time, and that is the assumption that our system is using the voltage of the supply of power, whether that be a 12 volt battery or a 12 volt power supply. To me that is like saying, well, my car's got 500 horsepower and I'm using all of that horsepower to cruise on down the road at 40 miles an hour. Now the first thing with pulse systems, whether it be pulse motors, solid state, getting accurate meter readings by placing your amp meter between your power supply and the motor is not a good way to do it. The meters most of the time do not like pulsed DC, even though you'll see most meters do have a pulsed DC signal. Does not mean that they're going to like a high frequency pulsed DC. The way to eliminate this, depending on your current draw to the system, will depend on the size of the caps you need. In this case we have 20,000 microfarads at 60 volts with these two hooked in parallel, which is quite ample to smooth out any pulses on a system that's drawing about 25 milliamps. Your two caps, this will become your power supply to your system. Your amp meter will then go between your battery or your power supply and your caps. So now the system will pull the pulses off of the caps and the meter will be reading a nice steady flow into your caps, and you will get a very accurate reading. The reading will be more accurate than trying to read the current draw of a simple DC motor. So that's the first thing you must do. Okay, so what we're going to look at now, you're asking why the caps across the resistors. Once again, it's a pulsed system. The caps are to smooth out the pulses, and the resistance is to work out our power consumption and our power output. So we will now start the starter up. As you can see, at the moment it's drawing 25.4 milliamps. We are going to go to the third decimal point in all of these tests, which will be quite accurate enough. Now the first thing I want to point out here is we have 12.6 volts at 25 milliamps is what we're using. That is the third decimal point. So if we take our trusty old calculator here, we go 0.025 times our 12.6, that's 0.315 watts. Now first, that is the first reason I don't believe we are using the 12 volts from the 12 volt battery. This is a half watt or 0.5 watt resistor, so it is already over halfway to its rated power dissipation capacity, and it remains cold. Absolutely cold, both of them. Now if that was the power consumption, as we would normally do our readings, our volts times our amps, this would be in fact getting warm, and it is not. It is absolutely cold. So that is the first reason I don't believe we are using our 12.5 volts or 12.6. The second reason, I have been mucking around with this for about, well, it's probably a total of 15 hours, and as you would have seen in the previous videos, the battery voltage did not drop within those 15 hours of testing I've done all up. It is high now because I did put a little bit of charge in it this morning, just to see what difference a higher voltage would make across the system. So at over half a watt in 15 hours, if that's what we were drawing from this battery, it most certainly would have went down some. Not a lot, but it didn't go down at all. So how are we going to verify the voltage within the system? We're going to use Ohm's law. Now Ohm's law says our resistance times our amps will tell us our voltage. So in this case our resistance is 46.3 ohms and our amp draw is 0.025 of an amp. So now times our amps by our resistance, so that would be 0.025 times our resistance of 46.3, and we get 1.157 volts. 1.157 volts. We measure the voltage across this resistor, which is smoothed out by this cap. The voltage is 1.163 volts. So that meter is telling us 1.163 volts. So 0.006 of a volt difference. So that is telling me that we are not using the potential 12 volts that we have within the system. This system here is only using 1.157 volts, or that, depending on which of those meters you wish to believe, but 0.006 of a volt difference between the two meters is pretty close. Meters may have a slight difference in accuracy, but that difference is absolutely nothing at all. So Ohm's law tells us that this system has only 1.157 volts, and our meter across that resistor also tells us the same thing within that 0.006 of a volt. So that is why I believe we are measuring things wrong. I touched on this once before, sort of got pushed aside, but since Mag's little experiment, this has brought about another way of showing that. So now we can see from this that 25 milliamps times our 1.1, we'll go in between, we'll say 1.16 volts, which is the middle of those two measurements, gives us a 0.029 watt power consumption. So now what we do is we take our meter off of our supply and we put it onto our output. Like I said, same resistor, a 0.3 difference, so we will use exactly what the resistor is when making these calculations. You'll see with that resistor across the output we have 2.212 volts. So our output is 2.212, and with a load of 46.6 ohms. So to get our wattage, we simply volts divided by resistance, so that will be our 2.212 divided by 46.6 ohms, and our output equals 0.047 to the third decimal point, 0.047 watts. So our input is 0.029 watts and our output is 0.047 watts. That is using Ohm's law. It is also backing that up using two different meters, which no doubt will have a very, very small difference in their accuracy, but as you can see by here, it is indeed very, very small. So that's what we have to show on there. So in regards to input and output, well, I'm going to leave that one alone, but that is what it is, as I've shown it. Grab yourself your calculator to do your own calculations as we're going through the video. Rewind it, try it again. If I've done something wrong, let me know. But that's what Ohm's law states. It is your amperage, voltage and resistance. If we have our amps input to the system and the resistance across the system, we can work out the voltage within that system. And as you can see, it is not 12.58 volts. So that's about it. I am still learning, but as far as I can work out, that is how you test the system using Ohm's law. Now, most of you are going to say, well, that's good, you'll be able to take the power off of that, put it into a battery and loop it back. Well, there's one big problem. On the output we have a 47 ohm resistance for a load. The internal resistance of one of these batteries is about 1.2 ohms. As soon as we hook it up to a 1.2 ohm load, the whole system changes. we can not remove this resistor and put a 1.2 volt battery across it, because once we take this 46.3 ohms of resistance out of the system, the only resistance we have within the system is the 0.6 ohms that is in this coil on the primary side that we are sending the current through. Okay, next. Alright, so we're putting that amount of current through the system. We're losing a very, very, very tiny amount, 0.6 ohms, with this coil, because it is thick braided wire and it is only 20 turns. So where is the extra coming from that's going in there? Well, there's one little thing we've overlooked. We have a secondary coil that sends a positive charge through our resistor into our base, which means we have a negative charge on this side. As you can see, diode, this is in this direction, so a negative charge can indeed flow that way, but the positive charge cannot, and that goes to the negative side of our cap. The positive side goes into the base. Now the current that's going into the base is additive to the current on the collector. So at a guess, I would say that is where the extra current is coming from, is our secondary coil, in this case 0.61 wire with 200 turns on it. So at a guess, I would say that is where the extra current is coming from. If I go and change the value of these resistors, just one of them, if I put a lower value here, this whole system changes and all the measurements changes, and our input current starts to get closer to the output current. If I go higher on this side than that side, the input current becomes less, and so does the output current. So at the moment it would seem the resistance value on both sides of the system has to be pretty much the same as they were within the light globes, which were the same, to be able to achieve the higher current on the output side. Okay, well, I think that's long enough. That's going to take hours to upload. One other thing, any guys or girls out there that are getting into this sort of thing, interested in this sort of thing, have a few theories of your own, come and join up and have some fun with the rest of us, and get to write out all this sort of stuff and figure out problems, or I shouldn't say problems, figure out what's actually going on within a system. So that's it for this video. We've done the test using Ohm's law. It was confirmed by the meters as being accurate. Other than that, I don't know what else to do just yet. But like I said, the resistors remain cold, so there is no way that there is 0.35 watts going through those 0.5 watt resistors. Alrighty, cheers from the Tin Man. Okay, you thought I was gone, but there was a little something I wanted to add. At the moment, I've hooked it back up to the battery. Going to do some more charging experiments. Now, the one thing we didn't look at is this primary coil is 0.6 ohms in resistance, and I want to point out that I do take into account that this resistance will go higher once this coil gets closer to some sort of resonant frequency. But the thing I wanted to point out is that what we must remember, it is this coil alone that is also producing the current that you've seen in the cap on this side. So it can't be going too much higher, otherwise the current would not be there to drive the resistive load that was across that side of the coil. So I did take that into consideration when doing the tests, and my point is, if this was going up too high, we would not have the current going back into our output side that we have. So like I said, this one coil is the primary source for our output as well as our input, and we are getting a little top off from our secondary coil going through this resistor and into the base, which in turn also goes back to the collector side of the transistor. Excuse me. So just something I wanted to throw in there. Yes, I did take that into consideration when doing the test, and because of the current coming back from this coil into our resistive load, really tells me that that is not going up very high in resistance, which is why I left that coil out of the calculations that we done. Right, thanks for watching. Cheers from the Tin Man.